Alright, so the problem we're solving is 1862.
Normal one is normal.
And the problem is basically a garage door that is attached to by a rope to a spring at the top. And there are springs on both sides of the door. And the problem starts off with the garage door flat, and then it goes down to a certain degree, which for this problem is 30 degrees. And we're asked to find the omega of the door at 30 degrees. The door is a thin plate, which helps us find I. And there are two springs, one on each side of the door, as well as the door standing from rest. So we know that original V is equal to 0. So to start off, the most efficient way to solve this problem, according to us, would be the work energy method. So the equation for this is, and so each of these parts comes out to T1 is equal to 1/2 m V squared. And this is the original V. And this ends up being 0 because V naught is equal to 0 as the door is starting from rest. V1 is equal to 2 because there's two springs times 1/2 kx squared plus mgh. And given where we put our datum, which is at the very top, the h for mgh is going to be 0, which brings this out to 0. And so we have V1 is equal to 2 times 1/2 kx squared. And then T2 is equal to 1/2 I omega squared plus 1/2 mv squared. So this is the rotational and kinetic parts of T2. And then V2 is equal to mgh plus 1/2 kx squared. With this being k original, and this is being x original, and this is the final x state. And mgh can be found given that we have a distance 8 over here. We have this degrees, but we need to find the final stretching of the spring.
In order to find the distance that the spring stretches, we need to find out how much this top length of rope changes. So we can establish a relationship between this length here and this length here. And so because we know that the total length of the rope doesn't change, we know that SA plus 2 of SB equals the total length. And then, therefore, we establish a relationship between the change in length. So that means delta SA, or the change of SA, plus 2 times delta SB is going to equal the change length of the rope. And we know that if the rope doesn't change length, this is just going to be 0. And so we can establish a relationship between these two, that delta SA is going to equal 2 times delta SB. And now in order to find how much the top length changes, we need to find out how much in 30 degrees of the rotation of the door SA will change. So we know that the door itself is 8 feet long, and it changes in degrees 30 degrees. So in order to find this length right here, which is SA, which is sine 30 equals 4. Because sine 30 is just 1/2. So that means we simply plug this back up in the equation up here. If the change in SA is 4 feet, the change in SB is going to be so we know the total length of the change in length of the spring from original is going to be 2 feet. And because we know it was given to us earlier, S1 of the spring was 1 feet, the original stretch of the spring. S2 is going to equal 1 plus 2. It's 3 feet.
Okay, just a correction to the equation earlier. There was a 2 here because there were 2 springs. And so as you just saw, we solved for x0, x0 and x1, where x0 is given as 1 foot and x1 is given as 3 feet.
I mean, we have to choose something.
So
I'm not sure.
now what we have to find is the H1 of the door to complete this potential energy at state 2.
So nothing gets.
We need to find the height displaced of the center of the gravity of the door. So we have the two free body diagrams of the door, one at theta equals 0 and theta equals 30. Theta equals 30, we need to find H1, which is the height of the center of gravity. So using, we know that, I'm going to draw a triangle here. We know that the length of the whole door is 8, but we also know that the length of from B to G is 4, so we can draw 4 feet. We know that theta equals 30. And so using trigonometry, we can conclude that this length, H1, right here, is 4 sine 30 equals 2 feet.
H1 comes out to be 2 feet. We can complete the V2 expression, which comes out to be times x1 squared. So x1 is equal to 3 feet, so we have 3 squared. The V1 expression simply becomes V1 is equal to 2 times 1/2 times K9 times 1 squared. To solve for T2, we have 2 unknowns at the moment. And this is of G because we're finding it for the body and not a certain point on the body. And so we would be using the center of gravity. And this comes out to being T2 is equal to squared. And so what we need to find now is omega and Vg.
Alright, in order to find the velocity of the center of gravity in the second position, we're going to use instant centers because omega is equal to the radius of the center of gravity to the instant center. So in order to do that, we're going to go over here. I've already drawn in the second position, A, G, V, and since it's 30 degrees, and from trig, we know that the distance between here and here, which is to A, is 4 feet. Alright, now another thing to remember is these A and B are running on tracks, which means B can only move to the left and A can only move down. So we can say velocity of A is in the negative vertical position, and velocity of B is in the negative x direction. And so from that we also know the radius, which is 90 degrees, is going to go down for this one and to the left for this one. So this is going to be our instant center. So we also know, we already know this is 4 feet. Because the center of gravity, since this is a smooth plate, we know that the distance from G to B is also going to be 4 feet. I'm going to move this over here. And this is a right triangle. The center of gravity, since this is all one piece, the radius to the center of gravity, or the instant center, is going to be right down here. So we have 4 feet, and we know that since this is a 30, 60, 90 triangle, this is 60 degrees. And since we know some geometry also, we know that when you have two sides that are the same length and the angles the same length, that these sides are all going to be the same length. So we know the radius to the from G to the instant center is also going to be equal to 4 feet. So now if we go over here, we have V of G1 is equal to omega times 4.
So these are all the expressions we have so far for the work energy, just because of our coordinate system, and the G is going in the negative direction. So what we end up with at this point is we just solved for Vg is equal to 4 omega. When we plug this back into the T2 expression, it comes out to 26.5 omega squared. So now we have all 4 of the expressions for the work energy expression, so what we can end up doing is just simplifying this all down and putting it all back into this equation, which is 0, T1, plus V1, which is solving for omega squared, or solving for omega, we end up with 1.82 radians per second. And this is the angular velocity of the door at the point theta is equal to 30 degrees.